today I wanted to do was take some time and review some of the motion graph stuff that we talked about on Wednesday at the beginning of class. So, first thing I'm going to do is I'm going to grab this graph, and then I'm going to grab these questions that go along with that graph. So, I'm going to cut this, and then I'm going to paste it on here, and then we're going to blow this up a little bit so it looks a little bigger, and I'll put this down here and make these a little bigger. And then I am going to give you 1 minute to discuss this graph and those questions that relate to this graph with the people around you. As you guys are doing that, I'm going to slowly write answers up on the board so you can check and see how you're doing. Ready? Discuss. Go.
I don't want to discuss. It's 4 seconds is 0. Oh wait. Position is 0 meters. And then position 5 is -3 times 0, 0. The time seconds, it's 0. Yeah. That means 0 to 3. 0 because of just a No. Yeah. Oh yeah. Velocity is. No, it'd be 1 meter per second. Yeah, velocity is 1. It just be 0 to 3. It goes 1 meter. Yeah, it'd be 1. I see 1 because it's 0. Started exactly velocity from 0 to 30. It's 0 because you start 0 meters. Then it's 0. Yeah. So it goes. You figure out that in seconds. Wait, is that displacement over time? Yeah, it's 3 divided by 3, which is 1. No, it's 3 plus 3 divided by 2. Just kidding.
All right, let's discuss. So, first thing we have to do when analyzing this graph and using it to analyze the motion of an object is make sure we know what we're looking at. So over here on the y-axis, this graph is labeled as displacement, meaning that this graph is telling us something about this object. What is that graph telling us about this object?
Displacement.
Which would answer what one-word question?
Why?
Not why, where. This graph is telling us where something is, okay? So the first question that's asking you for position, we said position is where at a specific point in time. So if we look up on the graph, right, we find it's asking you at 4 seconds. So this graph starts on the x-axis 0, 1, 2, 3, 4, right? So we see that at 4 seconds, that object is crossing back over the x-axis. So we would say that its position is at 0 meters. Physically, what does that mean about where that object is?
It's in the same spot.
It's in the same spot as that it started.
Could you just say that it's just at...
You could say that, that's fine, although numerically, if we're looking at measuring that motion, we would measure that as 0 because that's what we called the reference point. And you could say the reference point or where it started, that would be fine, okay? But then, for 5 seconds, we see that that object has come and is now down here, right? Where is that object on the graph? Well, it's below the x-axis, right? Meaning that we have to, it's important that we use the negative to represent direction. In reality, where is that object? It's the other way from where it started, right? It's behind where it started, or in the negative direction from where it started, okay? Average velocity, right? Average velocity relates to things. And this is going to be important later on, right? Average velocity is displacement over time. So we look at displacement in time. First, through this section right here, this object went up 3 meters, so it displaced 3 meters, and it did that in 3 seconds. So 3 meters over 3 seconds is 1 meter per second. Important that we put the positive.
Yeah.
Yes, because that indicates what?
That it's going in a certain direction.
In a certain direction. In this case, we'd say the positive direction, right? But when we look at average velocity from 0 to 10 seconds, what is the total displacement of this object?
0
for 10 seconds. 0, meaning that it ends up where?
It's original.
Right back where it started, right? I kind of skipped over that question. Didn't do that on purpose, but now it's working out. So the average velocity is 0 meters per second. Does that mean that the object never moved? No. But if you look at the averages, right? A positive velocity here, a negative velocity here, a positive velocity here, a negative velocity here. When you average all of them out, you get 0. Okay? Sure, go ahead.
For like, when you're finding the speed,
Yep.
would you have to put a positive or negative?
Speed, good question. If it says find the speed of the object from 0 to 3 seconds, do we need a positive or a negative? No, because speed is what kind of a quantity? Do you remember? It does start with an S. Scalar. Okay? Meaning that it only tells you how fast, but it doesn't tell you which way. Okay? So only when you're doing velocity is it important that you put the sign.
So like vector quantity.
Vector quantities, you need the sign, but scalar quantities, you don't. All right, good there? Next set of graphs, or next graph. There's the picture. There's the questions. Picture increase. Question increase. 1 minute, go.
The motion of from 0 to 4 is moving, moving motion. And then velocity from 4 to 10. Acceleration from 0 to 4 displacement over time. So it changes 0 over time. Velocity 4 to 10 seconds. It's flat, it doesn't move. No. Oh, wait. My apologies. 0 point less than 4. Oh, we just have to describe it. Average velocity is 0.4. Average acceleration is and the average acceleration is 4 to 10 I think is 0. Yeah, 4 to 10 is 0. Okay, it's something on the something on the something. I told you 0. Wait. I thought velocity was displacement. Wasn't velocity displacement over time? Oh yeah, you are. So the displacement is 4 at 4 to 10 seconds.
No, because that side is measuring velocity and that is everybody.
How do you find
All right, so let's discuss. First thing we said is important in terms of analyzing the motion of this object. Make sure we know what kind of graph we're dealing with, right? So what is this graph telling us? Velocity, meaning that it doesn't tell us where an object is. It will tell us what's it doing or where is it going or any of those fun things, all right? So during this first section right here, from 0 seconds to 4 seconds, okay? What do we see is happening to the velocity of that object? It's gradually increasing, right? It starts off at rest, 0 meters per second, and then the y values of this graph keep increasing until we get to there. Okay? But then, from this point forward, What do we see about the velocity of that object?
Constant.
It remains constant. It does not change. Does that mean it's not moving? No, it's moving. It's just not speeding up or slowing down. Okay? All right. Now, acceleration, right? We defined acceleration as the change in velocity over time. So if we take a look at the entire trip from 0 to 10 seconds, we talked about finding the change in velocity. You need to know two things. What do you need to know? Initial and final, right? We said that delta V is V final minus V initial. So we can rearrange that equation to look like this. So if we go back to our picture, what is the final velocity of this object? Not -4. It's +4, right? Because it ends up here, right? This is the final velocity of that object. The initial velocity of that object was 0. So on the top of this fraction, you have 4 minus 0. And then the amount of time that it takes for that to happen is 10 seconds. So that's how you get the 0.4. It's important there. The positive is important there because we said generally positive acceleration is going to tell us what about that object. If the acceleration is positive, that means generally that object is speeding up. Okay? It tells us how the velocity is changing. But during this section, right, during the blue section, what do we see about the velocity? It doesn't change, so the average acceleration is 0 during that section. Question? Sierra, go ahead.
Isn't the formula for average acceleration the same as for velocity?
No, because the formula for velocity, they look the same, but velocity is a relationship between displacement in time, not velocity in time. It's the change in position over time, whereas this one is the change in velocity over time. So in the first one, in velocity, you're changing where you are, but in the acceleration, you're changing how fast you're going. Okay? Sarah, that's going to be important when we move on to today's stuff. Okay? All right. Any questions about these graphs here? Okay. Let's move on, and we are going to start on the problem set that I gave you today that has the pictures of the ramps on them. So there's one side that has 1 or 2 ramps down at the bottom. We're going to start on that sheet. Okay. It says relationship between velocity and acceleration. Both of them say that, but we're going to start on the one that has the ramps on it. All right. Up at the top of that page, we start off analyzing non-accelerated motion. If something is non-accelerated motion, what does that mean? Not that it's not moving, it's not speeding up or slowing down or changing directions, okay? So it says here that this sketch below, which is not complete, shows a ball rolling at a constant velocity along a level floor. Non-accelerated motion and constant velocity are 2 ways of saying the same thing, right? The velocity isn't changing. So, it says the ball rolls from the first position shown to the second position in 1 second. So it goes from this spot here, let's try that again. This spot here, come on, circle. It's a little big, but that's all right. It goes from this spot here to this spot here over a time of 1 second. And it says that those intervals are 1 second apart. Okay? But then it also tells you that the 2 positions are 1 meter apart. Okay? If it then tells you to sketch the ball at successive 1 second intervals, right? What would we see about the separation of these objects over each 1 second interval? They should be exactly the same, right? So you would draw then the next one, I don't know, here-ish, right? And then the next one, here-ish, and then the next one, there-ish, right? Each of those pictures representing 1 second worth of time. So we just keep taking pictures of that ball at 1 second intervals. And because this object is non-accelerated motion, we should be seeing that those intervals keep remaining the same. When it gets to the wall, how fast is it going to be going?
The same speed.
The same speed, which we have established through, although we didn't officially do it. How fast is this ball going? 1 meter per second, because it says that in 1 second that object goes 1 meter. That being said, if this stretch of floor is 5 meters long, how long would it take that ball to reach the end? 5 seconds. Okay? Good there? Really hope that's all right. All right. That being the case, now let's slide down to the bottom. So now we start discussing accelerated motion. If something is accelerated motion, that means that it could be doing what? Speeding up, slowing down, or changing directions. Okay? For our purposes, because we're only dealing with 1 dimension, we're just going to deal with speed up and slow down. Changing directions is another story, and you get that in physics class. We're not doing that right now. But if we take a look at this ramp should look familiar to you, or at least somewhat familiar to you. You've done this experiment before, right? You did this when you did your lab report. Just like this picture up at the top, these pictures showing these objects represent 1 second worth of time. Ooh, hold on. They represent 1 second worth of time. We keep taking pictures of this ball as it rolls down the hill at 1 second intervals. What are you seeing about the spacing of the ball in each 1 second interval? Keeps getting bigger, because what does that ball do as it rolls down the ramp? Accelerates. More specifically, what kind of acceleration? It speeds up. Positive acceleration, meaning that it's going to travel a farther distance every second. Are we okay with that? Okay, that's the conceptual stuff. Now let's start putting numbers on it, okay? Because if we're going to measure motion, measuring motion involves dealing with numbers. So if we look back at your sheet, it tells you that the accelerated motion on this ramp is happening with an acceleration of 2 meters per second squared. That this ramp is tilted in a way that the acceleration is 2 meters per second squared. I am going to put this on a blank sheet because I'm going to draw all over it. You guys have some space around where hopefully you can fill some things in. So the problem told us that acceleration is equal to 2 meters per second squared. Now, we just discussed a little while ago, and we previously discussed, that acceleration is delta V over t, right? And so if we go back and think about it, right, what are we going to measure delta V in? What unit would we measure delta V in? Meters per second, right? Because it's a change in velocity. If we do 6 meters per second minus 0 meters per second, we get 6 meters per second, right? But then, on the bottom, we get seconds, right? And we said that we could simplify that unit into meters per second squared. That's what we did originally. We're going to kind of work backwards now. If I have given you, or this problem set has given you, that the acceleration is 2 meters per second squared, it's probably going to be more helpful to us for you to think about it like this. Does it make sense that 2 meters per second squared and 2 meters per second over 1 second are different representations of the same value? Is that okay with everybody? That those are really the same thing, just written in 2 different ways. Okay. That being the case, now let's interpret. What is that saying? If the acceleration is 2 meters per second squared, what does that mean to us? Lexi?
Between each interval you square the distance?
Kind of, although not literally. You're going to get there in a second, but that's not actually what an acceleration of 2 meters per second squared means. Okay? Eric?
Does it mean every second the distance increases by square?
It does not mean that the distance increases.
The
Lexi, what does it mean?
Between every 2 meters the time is squared.
Oh, I think that is it displacement?
Nope.
Interval that accelerates by 2 meters.
If it accelerates, okay, so Paige, you said for every second it accelerates by 2 meters per second. In this case here, Paige, physically, what is that going to mean for this ball? If it accelerates by 2 meters per second for every second, what is that physically going to mean here?
The distance between them.
What is acceleration telling you about?
Change in velocity.
Change in velocity.
It's gonna be double.
So what's going to, it's not the distance that's going to change, it's the what?
Velocity.
The velocity is going to change. How much is the velocity going to change?
Square. It will be
Two,
It's going to change by
4.
2,
2 for every
1.
second that goes by.
Wait.
Meaning, if we take a look at this ramp, each of these pictures represents 1 second worth of time. This ball at the very beginning started at rest. Velocity 0. The next picture we said represents how many seconds? 1 second. How much does the velocity change in that 1 second? By 2 meters per second. So the velocity after 1 second is 2. Good there? All right, now we have to make the next jump. What's going to happen in the next second?
4.
Why?
Because it's 2 times 2.
Sean, how much time goes by here? No, you're right.
1 second.
1 second goes by here. How much does the velocity change over that 1 second?
2.
By a value of 2. So it was at 2, now it's going to be
4.
next second. How fast is it going to be? 6. Next second, it's going to be 8. And then finally at the bottom of the ramp, 10. Now remember, that's how fast it's going. It has nothing to do with distance. It has nothing to do with displacement. That is how fast. Okay? What kind of relationship are we seeing here? What? It's increasing by 2. It's increasing by 2 every single time, right? What kind of relationship is that? It's a direct relationship, right? Sometimes we call that a linear relationship, right? Here's how we summarize that direct relationship. VF equals VI plus A times T, where VF represents the final velocity of that object, VI represents the initial velocity of that object, A represents the acceleration, and T represents the time. Now, in our graph here, we have a very specific situation. What was our initial velocity?
0.
0. So in our case, we're actually starting this object from rest. And if that object starts from rest, we can simplify that equation to look like this. Does that make sense? Because what's VI going to be?
0.
0. So we just get rid of it in the equation. And if something starts from rest, we can figure out how fast it's going if we know its acceleration and we know the time that goes by. we did it for nice 1 second intervals. But could we find out how fast that object was going at 4.274 seconds?
Yeah.
Yeah, we could, because we know the relationship. All right, is that good for starters?
Yes.
Okay. Page, go ahead.
So those equations are to do the final velocity.
That equation would allow you, Paige, to figure out how fast something is going at a particular moment in time. Okay? That would also, Paige, it would also count, like let's say we rolled the ball along a hallway and then it hit a ramp and then it started speeding up once it hit the ramp, right? That, in that case, VI wouldn't have been 0, but we could still figure out how fast something is going because we know the relationship. Okay? All right, good there. That's generally the easier part. Okay? So let's zoom in here. Nope. Let's zoom in to this little interval right here that I have circled in red. And I'm going to zoom in for you guys. If you're watching the video, you don't get the zoom in capability, but... All right, so if you're looking at this picture or you're looking at your ramp, you might be saying to yourself, and I know some of you are, I'm confused. Because this is labeled as how far? 1 meter. But I'm seeing a speed of 2 meters per second. But let's analyze what happened here. What did we say was happening to this ball the entire time? Speeding up, gradually, faster, 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 faster. It doesn't reach a speed of 2 meters per second until your stopwatch reads 1 second. The other previous 0.99 of a second, was it going 2?
No.
It was going
1.9.
less than 2. In order for something to go 2 meters in 1 second, it has to be going 2 meters per second the entire time. But it wasn't going 2 meters per second the entire time. It was gradually building up to that. Does that make sense?
Yes.
Okay.
Why do we need to know that?
Well, because now, Paige, I can't just do this. Okay? Because I can't just say, oh, a velocity of 2, a time of 1, displacement is 2, because it wasn't going 2 the whole time. This formula works great if the velocity is constant, but our velocity isn't constant. Okay? So, let's talk about some other math things. During this interval that we have right here, right, we know 2 velocities specifically. Which 2 velocities do we know?
Initial.
We know that the initial velocity was what, Lexi?
0.
And the final velocity was?
2.
We know that all those other velocities happened somewhere in there, but we know these 2 happened at specifically these 2 times. Does that make sense? Can we figure out what the average velocity was during that interval? If you know 2 things and you want to find the average of them, what do? Add them together and divide by 2. That works here as well. If we want to find what the average velocity was, we can take the initial, add it to the final, and then divide that value by 2. That's just taking the average of things. In this case specifically, what did we say our initial velocity was? In this case specifically, what was our initial velocity? 0. What's our final velocity? 2. So if we add 0 plus 2 and divide that by 2, what do we find out that our average velocity was? 1 meter per second. Because as it was gradually speeding up to 2 meters per second, half the time it was going slower than 1, And half the time it was going faster than 1. Good there? Does that make sense so far? Okay. Now, here's where it all comes back together. This is actually average velocity. This is average velocity as well. Same thing, calculated 2 separate ways. If A is equal to B and B is equal to C, A equals C. Right?
Yes.
Does that make sense? So now we can say that 1 meter per second from here is equal to delta x over t from here. Does that make sense? What did we say our average velocity was during this little interval? 1 meter per second. How much time went by during that interval?
1 second.
1 second. So how far did this object go? 1 meter. Does that make sense?
Where did it do that? It gave us.
It did give us that. I just want to make sure you understand why. Okay? Does that make sense? Because look, there's a bunch of spaces on that chart that they didn't give you. Right? Like this one right here. So let's take a look at this section right through here. Okay? Based on the discussion that we just had, what would be the average velocity during that interval? What would be the average velocity during that interval? Right. 5 meters per second is the average velocity during that interval. Ryan, how'd you get that?
I added the 2 velocities.
4 plus 6 divided by 2, right?
Yeah.
Okay. How much time goes by during this interval?
1 second.
1 second. This picture to this picture is 1 second. So, if we've gone on average 5 meters per second for a time of 1 second, how far is it between this picture and this picture? Okay. Is that good for starters? Okay. Here's what I want you to do over the weekend. I want you to do those 2 ramps, finish off the one we're working on now, and do the one underneath where I change the acceleration. I will post answers online. Those answers are for you to check how you're doing. I'm not collecting this, but practice is going to make it better. Come back on Monday, we'll discuss some more. Have a good weekend, everybody.